Okay. So let's go. I just want to check. Can everyone hear me currently? I'm having some
Yes, sir, we
audio
can.
issues. I just want to get a confirmation. What is that? Awesome. Okay, let's get started. So, this week we will be diving into a few different topics, largely to do with Python. And we'll discuss a little bit of why we're doing that as well. So let's see. So this week, we're going to look at loops and conditionals with Qiskit. If you already feel comfortable with these things, with these concepts, you can definitely let me know that, and we can move a little more quickly. And if these are completely new to you, or you've seen them before and still really just don't get it, then today's a great day to go over it. We will only really need these concepts for very specific purposes in this course and in general for quantum computing, really, at least for the kinds of things that we're doing. So don't worry about understanding all of these concepts in super depth. We're really just going to look at a few ways to use these to our advantage. So here's the agenda today. We'll do a little bit of Qiskit review. At this point, you've seen a lot of that. You've been doing it for, I think, nearly a month now. So hopefully you're feeling pretty comfortable with that. And I don't want to kind of, beat a dead horse, as they say. I don't want to go too in depth if we're feeling all right with it, but it's a good chance to ask any questions or anything like that. And then after that, we'll go into Python, we'll go into loops, conditionals, something called get-ran bits, and we might take a look at some lists. As usual, love to see all your lovely faces if you feel comfortable doing so. It was great getting some shots with everybody last week, and I know all the different groups did that, and it's been pretty fun to see the pictures coming out as everyone's adding them. The announcements, generally, the reviews, the office hours, I believe, are staying the same. Again, those are fantastic places to go to get some help or just discuss if you have questions, things like that. If you're using those and those are helpful to you, then definitely let us know so we know to keep doing that. And if there's something you think that would be helpful for you that we're not doing with those, then definitely let us know also. We also have some exciting events coming up. So first of all, we can all take a little break with the fall break from the 20th to the 26th. From what some people said, that sounds like perfect time to focus on FIFA if that's what you're into. And then when we return, there'll be an MIT lab tour. I know in the past, this has been a very popular and exciting event. So it's and really just an amazing opportunity. So I definitely encourage you to check this out if you can. And as usual, if you have any questions about Canvas or issues in general, you can always email student@qubit.org. This is today's attendance code. I will come back to it at the end, but I'll also leave it up for now so that you can go ahead and enter it on the website on Canvas. So attendance 7433, also sending it in the chat just in case I start moving on and you don't already have it. All right. Okay. So again, I put that in the chat as well, but let me know if you have any trouble getting that done. So I want us to take a moment before diving into all these details to just talk about why we're learning Python. We spent some time building these skills up in the beginning and have seen some of them in effect. So it may seem a little strange that we're after spending all this time talking about quantum computing and Qiskit, that we're going back to Python. But it turns out that there's a few concepts here that will be very helpful for what we're going to do next week. So next week, we're going to look at quantum key distribution involving these characters, Alice, Eve, and Bob, which you'll become very familiar with next week if you are not already. But learning about these protocols is, while it is exciting, it's never quite as exciting as doing it yourself for many people. And so really we want to end up looking at this and coding it ourselves. That's what we will all do together actually next week. And in order to do that, we'll have to write code like this. It may not look identical to this, but most of the features here are things that we will be touching upon next week in order to really implement what is known as QKD. So today is really about breaking this apart and making sure that you feel ready to do that next week, so we can really just focus on what we're doing, particularly from a quantum mechanical side, and so you can kind of appreciate why some of these concepts are important beyond just being occasionally handy tools. So let's get started. First of all, I want to do a quick Qiskit review. Again, I know we have seen a lot of these things over and over. So today is meant to be a very quick review and mostly a chance for you to ask any questions that you still have. If there's any little things or big things that are confusing you or you just are curious about, now is a good chance to ask that. We'll go through a few slides, we'll do some practice problems, and we'll kind of see where we land. So first of all, this is going to look very familiar at this point, hopefully. We have our 3 steps that we're getting pretty familiar with in Qiskit in order to create a circuit. So 1, you create the circuit, just an empty plain old circuit. And as we've seen through last week, we can add classical bits and quantum bits, and we can add different numbers. So for instance, in this circuit, we create an empty quantum circuit with 2 qubits. Qubits always go first. Again, this is Qiskit, qubits go first. And then the classical bits second. So this is a quantum circuit with 2 qubits and 1 classical bit. Then we can add gates and measurements. These are the gates we've seen so far. We can do an X, an H, a Z, or a CX. And I know that the CX, the controlled X or C0 gate, this is something that we only saw very quickly and is something that will take us some time to get comfortable with, at least in terms of what it does. But implementing it is not that much different from other gates. Because it's a 2-qubit gate, we do need to provide both qubits we want it to act on, in this case 0 and 1, but otherwise it's really identical to the rest. Understanding what it does and why is a more complicated thing, but honestly playing around with it in Qiskit is a great way to understand that and build some intuition for it. Then we can measure. And we've seen measurement for single qubit circuits and for multiple qubit circuits. Generally, you provide these lists. So just like when we create the quantum circuit, you provide the list of the quantum bits, the qubits first, that you want to measure in this case, and then the list of the classical bits you want to store them in, right? And then lastly, you can run or draw the circuit. There are a number of ways to do this. We kind of got a sneak peek of some of them last week, and we've seen a few already. Generally, we'll be sticking with the few that we've seen for a little bit, and eventually adding in using other simulators, using real quantum computers of different sorts, all of these things. But these are the 3 steps. This is everything that we've seen so far, more or less. And I would say that's actually quite a bit, right? I mean, a month ago, we hadn't seen any of these things. And by now, hopefully, these are starting to become very familiar. I do want to take a moment just to talk about the controlled NOT or the CX gate. Those are 2 different names for the same thing, since we did not get a chance to go too in depth last week. So one of the gates we can add is the CX gate. This is a 2-qubit gate where we have what is called the control bit and the target qubit, right? The control qubit in this case never changes. It never does anything, or nothing ever happens to it. Rather, it controls what we do to the target qubit, right? And this follows a few rules. In particular, again, the control qubit never changes. It's just there for the ride and just to call the shots. The control qubit controls what happens, but nothing actually happens to it. On the other hand, the target potentially gets changed. Now, if the control qubit is in the 0 state, then we don't do anything. So if the control qubit is in a 0 state, nothing happens. It's like the gate isn't even there. On the other hand, if the control qubit is 1, then we apply an X, right? So the control qubit is basically like a switch saying, are we off 0, and in which case we just don't do anything, or are we on 1 and do we do something? Do we apply an X gate or a not? The last thing I want to point out, that is a general thing, whether we use CXs or not, is if we have multiple qubits, it can be easy to lose track of which qubit is which. In general, in Qiskit, qubits are listed from right to left. This is a little different than we do in other contexts, so it's really important to pay attention to this and to just occasionally remind yourself of what's happening. So for instance, this first case here is going to be the most helpful. 1, 0 actually means that the qubit 0 is in the 0 state and the qubit 1 is in the 1 state, or at least that's where we measured it, right? So this is 0 for the 0th bit and 1 for the first bit. Those are the results we measured. We could also measure 1 for both of the qubits. That's fully fine. It's possible, in which case we don't have to really care which one's which. But in this case, it's important to know that even though this looks like 10 or 1, 0, really we read this right to left, top to bottom. Okay. Now, I know that was very quick, but again, we've seen these things. What I would love for you to do is open up the notebook, go to the quantum experience, and go ahead and take a look at these first few exercises. So go ahead and get your notebooks open. I can share a notebook in here as well, in case anyone was having trouble finding it. As usual, you can import from Qiskit. And then we have this section, Qiskit Review, that we're currently in. What I'd like you to do is exercises 1 through 2. Just 1 and 2 right now. These are slightly more challenging, slightly bigger circuits, but at this point, hopefully not too crazy. They do both involve the CX, which I know is a new gate. So give these a try, see how you feel. If you finish them before we come back together, you can also do the extra exercises here to kind of test your abilities. But really, if you're good with these exercises, then you're okay with what we've learned so far. So go ahead and work on these and let me know if you have any questions. I'll give you a couple minutes to do that. And as usual, go ahead and give me a thumbs up when you're done, or let me know in the chat. Okay. Seeing some people wrap up. So I'll give you another minute or so to wrap up and then we'll discuss. Okay. So hopefully that was enough time to start going through these first two exercises. Again, there's a third and a fourth just for extra practice. You'll also get more practice in the homework this week. You know, we want to make sure that you have plenty of opportunities, but I also know that we have seen these things a lot. Okay. Exercise 1. Let me go ahead and show you the solutions, but please let me know if you have any questions here. So for these parts, for exercises 1 and 2, let's look at 1 first. We create a quantum circuit with 2 qubits, and let me zoom in here. 2 qubits and 2 classical bits, 2 and 2. And then as it says, we want to apply an H to the 0 gate, an H to the 0 qubit, an X to the 1 qubit, an H to the 1 qubit, and then a CX. This is not a simple circuit, right? There's a lot of things going on here, multiple gates we've seen, multi-qubit gates, but it more or less reads just like we have here. One of the important things with the CX gate is to pay attention to which one is the control qubit and which one is the target. Usually we go in order, and we in fact choose which qubit is 0 or 1 based on this, but there's no actual real deep reason why we couldn't do a different way. And then we specify the list of qubits we want to measure and the list of classical bits we want to store them in. And then it's always good practice to draw your circuit just to confirm that you're getting what you want. So you should get something like this. Right, we see our H here, our X in our H, a C naught, and then a couple measurements here, one for each of our qubits. And then we can run this. Now we have a 2 qubit circuit. That means there's more states that we can deal with, right? In fact, all 4 of the possible states are here. There are no other possible states in this case, but it seems that we get a roughly equal breakdown. Of course, this is meant to be somewhat random, so you'll get different results most of the time. In most cases, again, I know some of us have seen more consistent results, which is nothing to be worried about, so long as you're seeing an equal distribution of these. But yeah, you notice there's an equal distribution, we get these out. We have a superposition here of all 4 states. Okay. And then exercise 2, it's really pretty similar, but in this case, we have 2 qubit gates, right? We have one CX with the 0 as the control, the 1 is the target, another with the 1 as the control, and the 2 as the target. One important thing here, other than making your circuit the right size, is to make sure you measure all 3 qubits here. We have a 3 qubit, 3 classical bit gate. It's 0, 1, and 2 in this case. And we can draw and see our beautiful circuit here. An H gate, a C naught, and 3 measurements.
May I ask a question?
Yes, please.
In the measurement part, why we write this 0, 1, 2 in twice time?
Ooh, this is a great question, right? You'll notice in measure, usually you write the same thing twice, even when we didn't have multiple qubits. The short answer is that this function measure was written so that you could specify qubits and classical bits differently. So this measures qubits and classical bits differently. We usually specify them at the same place. So the 0th qubit gets measured to the 0th classical bit. The first qubit gets measured to the first classical bit, so on and so forth. That's just our choice to make things a little simpler so that we understand what's coming out. But if you wanted to do something different like this, you completely could, right? It would measure, but the results would then be a little strange, or at least harder to interpret. Now, in this case, the answers are all the same for them, so it doesn't totally matter. But the point is that, for instance, you'd measure the 0q bit and store it in the second classical bit. And I don't know about you, but this feels like it would get very confusing very fast. So it's just good practice to keep them the same. But it is important to understand that they represent different things. The first part here is the Q bits you want to measure, and the second part is the classical bits you want to store those results in. So they represent different things, but just for ease, we keep them similar or the same. Yeah, that's a good question. Do we have any other questions about this? Yes, please.
Yes, sir. Can the control qubit be the first qubit while the target qubit be this? Can the control qubit be the second while the target qubit becomes the first, like QC.CX, then 2,1?
Ooh, yeah, that's great. Let's take a look. Yeah, indeed you can. There's no specific order to this. Again, for our sakes, we tend to choose a certain direction, like we usually go down, but there are actually very real cases where you might want to do something like this. And in fact, you might do them back to back like this or something like that. So 100% you can do this. Always glad to show those cases. I'll also say these are great kinds of questions, and I encourage you all to try these things out. Like if you're wondering the limits of this, really the best programmers are the ones that almost try to break the code that they have so that they understand what it can and cannot do. But yeah, totally no special thing about C-naughts going down like this or anything like that. They just listen to whatever you tell them for controls and targets. Okay. Any questions otherwise? Any other questions? Great. Okay. So now we can go back here. And I just want to stop again. I know I asked for questions. Are there any questions generally? And how are we feeling about these topics? I'd be curious to hear in the chat. Are we feeling comfortable with this? Does it still feel kind of confusing? Where are we at with this? Feel pretty comfortable, thumbs up. Okay, that's good. Still kind of confusing. Yeah. Okay. Yeah, it's okay if you're not feeling 100% on this. Smooth like butter. That's a good one. I love that. You're still not feeling totally comfortable, but again, we'll keep practicing. We'll keep going through, and we'll all kind of continue learning new things. But I'm glad to hear that on average, no one is completely flailing or feels just completely uncomfortable with this, has no idea what's happening. If you are feeling that, definitely reach out so that we can, hopefully get you caught up and make feeling good about it. But I get the sense that we're doing all right. So I want to talk about some new concepts now. First, I want to talk about loops. I want to learn about loops. Well, as we start creating more complex circuits, we really already can do that with what we've learned. But you can imagine that these might start getting really, really big. We might start having things that we're doing over and over again in all these different ways. And to make these more complicated circuits that are really big, it might be helpful to have some certain tools here. For instance, imagine you're writing out every single gate for something like 26 qubits, and you want to put them into the plus state. That would be 26 different lines of code to more or less just say, put all the 26 gates in. We would ideally have something that would make this easier so that we don't have 26 lines for this, which might make your code harder to read. And might mean maybe you accidentally type an X on one line or a Z or a J or whatever, just some mistake that's hard to find. And we can save ourselves a lot of time and effort by just doing something simpler. So for instance, we could try doing this and list out all 26 of these, or we can use a loop. Condense all 26 lines into just 2. This is the tool that we're going to see today, and this is going to turn out to be very, very helpful. Okay. So let us see. Okay, so a loop. This is used to execute the same code multiple times. So it has to be the same code, but you can repeat it multiple times. There are actually several different kinds of loops. For those of you that have more background with Python or programming, you may be well aware of these different ones: while loops, do whiles, for each, things like this. And it's different in every language. For us, we're keeping it simple. This is what a for loop will look like for us. We do not need to go beyond that. What this does is, it says we're going to repeat this code some number of times. There are a few pieces you need for this. For instance, you need to specify you're using a for loop. That is the name of this type of loop. So you always do for, all lowercase. You need to write whatever code you want to repeat. Without this, there's no point to using a loop. So this is the code you want to use. And an important part for Python is that it needs to be indented. Notice that we have nothing over here to the left. It needs to be indented so Python knows what code you want to repeat and what code may come later. And then don't forget this colon. That's just a super simple thing that's easy to forget. And you could end up spending a lot of time not realizing that the reason your code isn't running is just a missing one of these colons. So just a good one to remember, as well as the in. So let's look at some examples in order to really start to understand what this does. So again, the general syntax here is provided, and let's look at this particular example. What do you think will happen? I'm curious. Go ahead and say in the chat, what do you think will happen? Feel free to say in the chat. We'll print hi 5 times. Yeah. Awesome. Yeah, we got it. It'll print hi 5 times. It'll print hi 5 times. So what we're saying here is for index and range 5 means repeat 5 times the command print hi. Remember, we saw this print function, this print command, which takes in whatever you give it and prints it out to the screen. So really all we need to know is, hey, I changed this number to be 5, and that tells me I will do this 5 times. 1, 2, 3, 4, 5. Let's look at another example. Let's say I do this. What will happen? Notice a few things changed here. What do we think will happen here? So in fact, what will end up happening is 3 times over, we'll print hi and then bye. So hi, bye, hi, bye, hi, bye. So you can have multiple lines here, and that's an important point. You don't have to just put 1 line of code. You can have as many lines of code as you want. So long as they're indented, they will repeat this number of times. So what happens if we actually print this thing? We haven't really talked about this yet. There's kind of this mysterious index, for index and range 5, print index. What do we think is going to happen here? What do we think is going to happen here? Okay, yeah. I think we're getting the hang of this. Yeah, let's take a look. It'll print 0, 1, 2, 3, 4. That may not be obvious. It's okay if it isn't. Hopefully you recognize by now, well, okay, we print 5 times over. The key thing here is range of 5 gives you how many times you will print or do whatever is in here. So notice there's 1, 2, 3, 4, 5 things we print, but we start at 0. It turns out that just like lists, when you do this, this index variable starts at 0. Right? In computer science, a lot of things start at 0. We start counting at 0. So in fact, we count from 0, 1, 2, 3, 4. This is a very important part. To give you some language, this index here, this is called the loop control variable. That's some technical terminology because it controls the loop, basically. Or it's controlled by the loop, I suppose. What it does is it takes on each value in the range you provided one at a time. So it starts at 0. It always starts at 0 when we have this. And then it goes up by 1 every time. 0, 1, 2, 3, 4. So let's see a more complicated case using lists. I know we haven't looked at lists in a little while, but this might be a good refresher. What will happen here? What will we print? What will we print here? Awesome. Okay, yeah. So we print hi. Keeping in mind, we have HI and the exclamation mark on different lines because this is called one at a time. So we print the first character here, or really I should say the 0th character here, or string, H. Then we go to the 1, the first, and then the second. So 0, 1, 2, we print them out one line at a time. So we don't have to do the exact same thing every time if we're clever about this, particularly using things like lists. And if we use this loop variable here. Now, what if I just have the same code, but I change this to Bob? So no longer index, this fancy sounding index, but to Bob. Is this going to be a problem? It turns out it's totally fine. It's actually no different. So the name of this variable does not matter. The loop control variable is truly a variable. It's all it is. It follows the same naming rules as any other variable. You could name it Bob, you could name it Alice, you could name it whatever you want, so long as it follows the typical rules for variables. We use index to try to be helpful because it's good to have useful, meaningful names, but you don't actually need to name it index. For instance, sometimes with quantum computing, you might call this 4-qubit in range 3 if you had a circuit of size 3 or something like that. So you can name it different things, and I'd encourage you to be thoughtful about that. What names make sense? Okay, so let's go ahead and do this. We'll complete a couple exercises together, and then I'll let you work on a couple on your own. So let's go through to part 2 here. So notice we're skipping the extra exercises in the Qiskit review, and we're jumping into loops. So you should see something like this. Exercise 1 together, let's write code that prints the numbers 0 through 9 using a loop. You've been given some of the code already, but we do need to finish this. In particular, for I in range something, we need to finish this line. There's 2 lines. We want to in particular print the numbers 0 through 9 using a loop. Now I'm curious, does anyone have an idea of what this might be, what we want to fill in there? Ooh, okay, yeah. Nice, yeah. Couldn't trick you up. Indeed, it's 10. You want to be careful. It's not 9 because 0 through 9 is actually 10 numbers. So this is the number of things we'll do. So we go here, and then based on what we've said, I see Krish has said, let's do print of I. Ooh, you got me. I was hoping to catch you on that, on the colon. Yeah, we need the colon there. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all on their own line. So the beautiful thing about this is you could change this to some crazy large number and it'll print them all out. But notice how easy that was for us. We barely had to do anything and we can get a lot of different results. We can get many results all at once. But all we have to do is change this number, right? So if we want to do it correctly for this problem, we do range 10 and we print, make sure you have that colon. It's such an easy thing to forget. Okay, now let's do exercise 2 together. So let's write the code that prints all 4 elements from the provided list. So we have a list provided here with 4 elements, and we want to print each and every one of them. So provided the list, but now I want you to write, and we will write, the whole for loop together. So first of all, you want to say, hey, I'm using a for loop. So for. We need some sort of variable. Call it index. I works. I is another typical one, short for index. We need to say in what range. In this case, it would be, we want 4 elements. So I've already told you 4 elements. And then we can print out my list of index. And I will say this is not the only way to answer this. There are other ways, but for our purposes, we really only need to know this one structure. If you know of other ways, totally fine. Feel totally comfortable doing those other things. But for our purposes, if you're not familiar with these, this is new to you, just use range, say the number. It's very straightforward. There are more advanced ways to do this. Awesome. Okay, so work on exercises 3 through 5 here, and I was just going to say I'll be here for questions. So yeah, go ahead. Yeah, what's your question?
Okay, could we use the foreign range to write my list in just in a one line?
Ooh.
So not in the different
Yeah.
lines?
Yes, that's a great question, right? You notice like, hey, this is great because I didn't have to write out every single one of these, but it's kind of annoying sometimes that these come out on different lines. So yeah, it turns out, and this is totally not necessary knowledge, so focus on getting the for loops down. We can add this bit. We can specify how we want to end each line or each print command, and then it all goes on here. So right now I have a space. If you don't want that, you can do this. So you can specify whatever you want here. So notice now I put an S here, I'll do an X to make it even clearer. And notice that that comes out at the end. Yeah, there's all sorts of things you can put in here. Basically, there's an extra parameter you can pass to print to say how you want to end. But the automatic one is just a new line, sometimes called \n. You don't have to deal with that here, but if you're curious because it's just bothering you, which it does bother me sometimes, then totally you can add the end parameter. Yeah, it's a great question.
Thank you.
So yeah, work on exercise 3 through 5, and as normal, let me know in the chat or with a thumbs up when you're done. Okay, seeing some folks are starting to wrap up. Okay, why don't we discuss? So let's scroll down to the loops. So again, we looked at exercises 1 and 2. We can also look at, there we go, exercises 3 through 5. So for exercise 3, we want to write code that prints all 10 elements from the provided list, right? This actually is going to be very similar to what we had above. We just have to change the number. The beautiful thing is that although this is a different list with a different data type in it, these are ints as opposed to strings, and it's a different size, we actually don't have to change the code very much. That's something that's a very good sign in computer science, when you can do a lot of things with very little change. So this is very powerful, kind of gives you some sense of what we'll be able to do with this. The general structure is for I or index or whatever you want to call it in range. We have 10 elements, so we do 10 and then print what? Well, my list indexed at I. And again, you could call this index if you wanted. You could call it Bob, you could call it Adam, you could call it whatever you want. Exercise 4, very similar. You don't have to print out the whole list every time. You could just print out some of it. So we actually don't change anything in the code except here in the range to say how many elements we want to print out. In this case, we just want 5. So also run these just so you make sure you see them in action. And then when we run this, notice we only get through the first 5 numbers. Okay. Now this one's a little more challenging. We have multiple things we're doing and kind of different nuances of printing that we have to be careful of. So here's the solution. First of all, set up the for loop. That's usually the easiest part, and it's a good one to start with. Just set it up. How many things do we want to print? Here there are 12 of them. So we do for I in range 12. Then let's fill out what's in here. So we can, for instance, do print, we say index, and then we need to add in what index we're at, where as the hint reminds you, you have to be careful about printing an int. And so we wrap it with string. And then the next line is actually pretty similar to the above. And so we get out this result. Okay. So let's now go back and see some more things we can do with this. Now we've seen these with Python at this point, but let's see it specifically with Qiskit. It turns out it's really no different when you're using Qiskit. So say you have a quantum circuit with 26 qubits and 26 classical bits, a very large circuit, not just for us, but in fact for most people. That's a very large quantum computer by today's standards. Some of the largest ones are just over 100 qubits for what it's worth. But let's say we make it 26 qubits. We don't actually have to change very much here. For index in range 26, because there's 26 of these things, and then we can apply a gate. So this is actually the answer to the question that we had in the beginning of what if we want to apply an H gate or prepared plus states for 26 different qubits. Note that we can do more complicated things too. For instance, we could apply C0 gates that basically cascade down, where we go from 0 to 1, 1 to 2, 2 to 3, all the way down to 24 to 25. So we can get pretty complicated with it, but notice that the setup is always the same. And that's the beauty of using loops here. So let's go through one of these together and then we can practice. So exercise 6, let's do this together and then you can practice. So we want to create and draw a 4-qubit, 4-classical bit quantum circuit. Sorry, I'm showing the solutions, but I guess I'm going to walk through them anyway. So where we apply an X gate to each qubit using a for loop, and we measure all the bits. So let's walk through what the solution looks like here. First, we need to create a quantum circuit with 4 qubits, 4 classical bits. Hopefully this is becoming more familiar at this point. 4 qubits, 4 classical bits. Now the new part here is that we want to loop through and apply an X to each. We could write out QC.X of 0, QC.X of 1, so on and so forth. But even for 4, it's a little nicer just to do this. We save a couple lines of code. And if we had more qubits, you can imagine it would be a big difference. And then we measure all of them. So we can run this and look, beautiful. We get this circuit where we apply X's to all of them, even though we never actually technically wrote QC of 0 ourselves. We had Python do that for us. And then we can run this. And hopefully, unsurprisingly, if you take a moment to think about it, we get out all ones here, all ones. Okay, so let's take some time to work on the next few exercises. So we'll go through, you can go through the next few exercises. Starting at, where are we? Exercise 7. So you can go ahead and start at exercise 7 and do that one and the next one. So 7 and 8 here. Give your best attempts to it. It's okay if you're not fully able to get through, but give it your best shot, and I'll give you a couple minutes to work on that. So exercises 7 and 8 here. And ask me any questions you have. If you're feeling a little lost or unsure, it's a great time to ask. If you're feeling like this is just totally comfortable for you, then that's all right, or potentially help out others who are a little more lost.
Sorry, Adam, can you show the exercise number 6 another time?
Yes, absolutely. Let's see, I believe that skipped ahead a little bit. I don't know why. All right, exercise 6, here we are. Yes. Do you have a specific question, or you just want to look at the solution?
No, just have a rapid see of the exercise because I've missed that step. So
okay.
Yeah. Thank you.
Yeah, no problem.
Could you please tell that a little bit more? Because I'm just a little bit confused about it.
Sure. So why don't I start by showing what we would do without a for loop. So if we didn't use a for loop here, and I'll move a little quickly, but we would end up with something like this. This is what the code would look like if we didn't use a for loop. What we can do is accomplish the exact same thing using a for loop. Now, before I go there, does it make sense what this code is doing, or at least that it matches with what we're being asked to do? So hopefully this matches up with what we understand we're trying to do. We have a 4-qubit, 4 classical bit circuit. We apply an X to each qubit, 0 through 3, and then we measure all the bits. We'll notice that if we run this, we get out the exact same circuit as before. But now what I'm saying is we can use this handy new tool called a for loop to basically just combine all these lines, to just make it a little simpler. Notice that all of these lines are the exact same. The only thing that changes is which qubit we apply it to. So what I'm saying is basically this for loop offers us a way to do that, where we can say for index, or you could call it qubit number, qubit index if you wanted, in range 4, and do this. Where the important parts are, we have 4 some variable, again, this could be called anything you want, in range of however many you want. This is going to look the exact same for us every single time, except we just change the number and potentially the name if you want. But if you wanted to keep this index every single time you wrote a for loop, that would be completely fine. So we can just keep it like this if you want. So it'll be identical. The only things you will ever change with this are the number in here, which says how many times you want to go through, and whatever you want to put in here. And here, index starts at 0, then goes 1, 2, 3. So what this says is, okay, for index and range 4, we'll do this 4 times. qc.x of 0, qc.x of 1, qc.x of 2, qc.x of 3. So this is just a way to just take that exact same code we had before and wrap it up. And again, if we run this, the circuit that comes out is no different. We actually haven't done anything different in Qiskit or created any different quantum circuit. There's nothing new here in terms of the quantum circuits. The only new thing is the way that we're making them. We're just defining them a little more compactly or in a smaller space. So these things will take a little bit of time, but yeah, of course, but hopefully they're coming through. All right. So again, we'll keep looking at these, but for now, I would just love to hear how you're feeling about these. How are we feeling about these at the moment? Are we feeling okay about them? Really, where are we on this spectrum? And I'm assuming that we're all going to be in a different place, and that's okay. So basically, how are we feeling on loops in particular? Okay. And Umar, I see that you're expressing feeling a little stuck on exercise 5. I'm glad to stick around for a moment afterwards to look at that specifically. We'll also release solutions. I'm definitely glad to go through that a little bit. We'll keep moving for now and know that these are some extra tools that will make things helpful. But again, I do want to emphasize at the end of the day, we can technically always get away without them. It's just going to make our life a lot easier. Okay. So let's move on to conditionals. We only have a few minutes left, so I want to get to the key parts, and then we can leave it there. And again, we will have time to look over these next week. You'll have time to review them for homework, but let's at least see what they are. So it turns out that for some quantum algorithms and protocols, including the one we're going to see next week, QKD, you don't always decide what gates you're going to use until you're already in the middle of running them. So this is another option. This is how we do it. We need to use some comparisons to basically compare, hey, what situation are we in? And then something known as a conditional statement, which conditional on the comparison result, we do different things. I just want to quickly go over, remind you, we have all these comparisons, these operators. You can always look these up. They always return true or false, which is called a Boolean. Is the comparison true or false? Apples greater than oranges, true or false? And now the new thing is that we can use a conditional, or sometimes called an if statement, because that's usually how it's written, to perform different actions depending on whether a condition is true or false. This is a way to write code that will happen sometimes if something is true and do something else otherwise. We have two options. We can either just say if something is true, if condition is true, then run some code, or we can provide an option where we say if condition is true, then do this, run this code, and if it's false, then do this other thing. So for instance, in this example, we'd print high because 5 is greater than 3. That is true. So we print high and we completely ignore this code down here. This is completely ignored because 5 is greater than 3. However, now we're saying is 3 equal to 5, equal 5. This is false. So in fact, now we do the other one. We print 5. Print high just gets completely ignored because 3 equals 5 is not true. We can get a little more complicated and do different things depending on the case, including changing variables. So in this case, we actually wouldn't print anything because my var is not equal to apples, but we would actually change the value of my var. So let's go through and complete exercises 3.1 through 3.3 together and take a look at what this looks like. So, and actually we'll just complete a couple of these and we can have more time to look at it next week. So in this first exercise, I'll go ahead and show you the solutions here. In this first exercise, we want to print code that prints "you can drive today" if the variable age is over 16 and prints "I'll be driving otherwise." Age is the variable and we can compare it to the value 16. So we're saying if age, the value of that variable, is greater than 16, we do this, print "you can drive today." Else, otherwise, we print "I'll be driving." So in this case, age is set to 12. They're not going to be driving. And every single time we run this, it'll be the exact same result. But the moment that I make this over 16, it changes. "You can drive today." And we completely ignore this other part. So it runs one bit of code or another depending on the condition. We can do more advanced things, like we can modify a list. Or, and I'll just skip ahead just to make sure you see this and get some get to see this in action, because we'll get to see this even more next week, but it's pretty cool, I think. We can actually do something like this, where based on a variable, we make a comparison and we set up a different circuit depending on that comparison. So in this case, we have a variable called choice, and we say if it's equal to not, equal not, then let's do qc.x of 0, as in apply an x gate. Otherwise, we'll apply an h gate. So if we run this currently, it applies an x gate. And every single time I run this, it's the exact same circuit, nothing different, nothing special. The beauty of this is that I can change this up here, and I can say choice is whatever else I want it to be. Let's just call it Adam. In this case, now it switches to an h gate. And every single time I run it, I get an h gate. Because now Adam does not equal this string. So we go here else. And this is a way to make a different circuit depending on the outcome. Now, I know that we didn't get through all of that, and we will have more time to see this next week. This is really meant to be an initial look over these things, these concepts. I would also like to focus on the fact that this is a quantum computing course. These are valuable tools, but they're not the core pieces. So this week is really a chance to see some more things, some more ways to just kind of get more advanced with your circuits. We'll see them in action next week. You'll have more chances to practice. But I do want to let you go since we're at the time now. Have a lovely week. Feel free to stick around if you have any questions. Otherwise, I will see you all around. And again, we'll have more of a chance to practice next week.
Okay, so may I ask a question?